Hello calculus fans, and welcome to section 6.1 where we talk about the areas between curves. So just as a little review here, if you remember in calculus 1 we would find the area between a curve and an interval on the x-axis. So we'd have something like, we'd have our x-axis here, and we'd have this curve y equals f of x, which would maybe go something like this. And we'd be interested in the area under this curve above the x-axis between a and b. If you remember, we found that area and we ended up just integrating the function between a and b to do that. Okay, so we're somewhat familiar with what we're going to do here. This time we're just going to, it won't necessarily be the x-axis here. The bottom could be another curve. So instead of integrating between this curve and the x-axis, it'll be between this curve and some other curve. Okay, but the main idea will be very familiar. So more formally, let's consider this curve here, y equals f of x. We've got our x-axis here, and we're interested in the area underneath this curve between a and b once again. So we've got between a and b. We're looking for this area here. And if you remember in calculus 1, what we did is we just broke this up into a bunch of rectangles. We'd have it'd be evenly spaced here, so there'd be this little gap here, which we would call delta x, and each of those would be equally spaced, and we'd essentially have a bunch of rectangles. Here we'd find the area of the rectangle, so we could use like left endpoints, right endpoints, midpoints, or whatever we need to do to get the height of these rectangles. So in this case, I just use the midpoints. So we would look at this first rectangle here. We'd find the midpoint of the rectangle and go up to the height of that, and we'd use that for the height of the rectangle, right, using the midpoint. So this one would come across like this. This one would be something like this. And this one over here on the end would go something like this. All right, we'd then find the area of these rectangles using the midpoints of each rectangle to find the height of the rectangle. And then just some of the things that'll be familiar. We wanted to find this little gap, delta x. We would always say something like delta x equals b minus a over n, where n would be the number of these little subintervals, the number of rectangles we're going to use, right? And then the distance would just be this number, take away that number, divided by how many pieces there are, and that would give this gap delta x. And then we would typically label these points, so we would have x. A would typically be x sub 0, then we have x sub 1, x sub 2, x sub 3. B would be x sub n, so this would be x sub n minus 1. And if we just put, let me just draw a typical rectangle in here, which we'll use. And again, if I use the midpoint for this one, we would have this rectangle here. Looking for the area of this rectangle. So then this distance here would be f of, let's say, x sub I star, because it could be any sample point. We're using the midpoints here in our demonstration, but it could be really any point. Left end point, right? We could have picked the left end point, the right end point, the midpoint, or any random point. A lot of times they use this x star to represent any random point in here. And as long as we take the limit, it doesn't matter what we use, right? If you remember from Calc 1, if we're going to use an approximation, we're going to use a certain number of rectangles, then we'll get a little bit different answers, little variations in our answer for the area as an approximation if we use a left endpoint, right endpoint, midpoint, or any sample point. But if we take the limit, then it's not going to matter. We're going to get the same answer regardless of the sample point we use, because we're going to get the exact area under the curve once we take the limit of these Riemann sums. Okay, so let's see, one more thing just to make it really clear. So this distance here would be delta x, and then you can see we've got a formula here. The formula for this rectangle is just base times height, which is going to be delta x times f of x sub I star, right? So that'd be the area of any one rectangle. And then so to find the area, what we do is we would just take the limit as n approaches infinity. And basically we take the limit of these Riemann sums, the sum from I equals 1 to n of f of x sub I star times delta x. Right, so this is just the sum of all of these height times base, right? The area of each one of these rectangles. We take the limit as n approaches infinity. So it'd be like, maybe we're going to add up 1,000, break this up into 1,000 pieces and find the area, the approximate area using 1,000 pieces, then maybe 1,000,000 pieces and 1,000,000,000 pieces. We're looking for the limiting value there, right? And that limiting value will actually give us the area under the curve. So in section 5.2, we did a few of them like this in the homework, and we saw this is a limit of a Riemann sum. It's a lot of work, but then we used the fundamental theorem of calculus, and we said we can, instead of this, we can just integrate this function f of x dx. As long as we know an antiderivative, we'll be able to find the answer simply by plugging in the endpoints and subtracting. So this was a much easier technique using the fundamental theorem of calculus. And then this is the limit of Riemann sums, which is a lot of work. All right, so that is what we have done in the past, right? Typically at the end of a Calc 1 class, you start talking about integration, and you'll talk about this. And of course, this area here is referring to the area under this curve between A and B, right above the x-axis. And this is an equal sign, right? Not approximately equals, exactly equals. The limit of these Riemann sums is exactly the area, right? And this also is exactly the area. If we integrate this function, f of x between A and B, we will get the area underneath that curve. Okay, hopefully this is bringing back some fantastic memories of Calc 1. If not, if the memories were not so fantastic, this could be the beginning of a long section. But hopefully it won't be too bad. Okay, so if you recall also from Calc 1, if this function is positive, so f of x is greater than or equal to 0, and it's continuous on A, B, and this is always going to be a requirement in calculus. Calculus is continuous mathematics, so the functions will always be continuous in the intervals that we're interested in. Then the area between the curve, y equals f of x, and the x-axis. In other words, we can start to think of the x-axis as a curve y equals 0. From x equals a to x equals b is this integral here, okay, which is kind of what we just talked about. So we've got this integral, which represents the area under the positive curve above the x-axis. So the picture we've got here for this statement here is just this. We've got dx. You could think of dx as, once the limit of the Riemann sum has been taken, this dx is change in x is sort of like an infinitely small change in x, right? This dx, and then this is still f of x, still the height. So you still have like base times height here. You can still sort of interpret it that way. And here we would just take the sum of all of these f of x dx's from A to B. And again, the bottom curve in this case is y equals 0. Right? So we can see this in the picture. Also, if we just think of this as like a really infinitely thin rectangle, and we have infinitely many of them because we're taking the limit of those Riemann sums. Okay, so what we're going to do in this section is we're just going to extend that case, as I mentioned, so this bottom curve won't necessarily be y equals 0. It'll be some other curve. And there's really only 3 things that can happen And it turns out easier than even that, because all three cases end up being the same integral, as we'll see. So let's take a look at the three cases that are possible. So I sketched them in here, and you can see basically the three cases are this. Case 1, f of x and g of x are both positive functions, so they're both above the x-axis, and we're going to find the area between these two curves. Case 2, you've got f of x, which is positive, above the x-axis, then g of x is a negative function, so between a and b, g of x is below the x-axis, so we're going to find the area between these two. And then finally, case 3, f of x and g of x are both negative functions, so they're both below the x-axis, and we want to find the area between these two curves. Now, as I mentioned, in all three cases, although they look different, when all is said and done, there's going to be one technique that works in all three cases. So we don't have to memorize or remember about remembering three different cases. The same technique works in all three cases. So what we're going to do today is just convince you of that. We're going to look at each of the three cases, so you'll see that we use the same technique in each case. Okay, but before we get started, in case you're getting sleepy, I have to torture you with a horrible joke to wake you up. And these jokes are horrible. And this is the bad thing about teaching math. Everyone you've ever met will send you these horrible jokes. And that's what I do. I share them with my students. They're so bad, they sting a little and they wake everybody up. So here we go. Are you ready? We're going to want to write this one down so you can torture your friends with it. Did you hear about the mathematician who's terrified of negative numbers? No? Turns out he'll stop at nothing to avoid them. Yes, you heard that. He'll stop at nothing, like 0, to avoid them. Yep, I know. I'm probably not hearing much laughter, even if I could hear your response. But that's my life, guys. It is not easy being me. These are the kind of jokes I get sent every day because I teach math. So I'm just going to share them. When they come in, I'm going to share them with you so we can both suffer a little bit from these horrible jokes. But okay, hopefully that stung a little and you're wide awake now, ready to look at the area between y equals f of x and y equals g of x from x equals a to x equals b. And you'll notice, looking at the picture here, these are both positive, right? So case 1, we're on case 1 right now, which is where these are both positive. So you can see just by looking, they're both positive. They're both going to have positive y values that are above the x-axis. So what we're going to want to do is do what we always do and break this up into pieces. And we want to figure out, what we'll do is we'll take a little sample rectangle. So let's say we have this little sample rectangle here. And we want to find the area of our sample rectangle. Okay, so let's just kind of go over here. We'll do this. So we want to find the area of our sample rectangle. Because then what we're going to do, once we find the area, we'll just sum all of those, right? We'll add up all the sample rectangles. So basically, a rectangle's area is base times height, okay? We know that. Well, we know that as long as you studied in 2nd grade, so hopefully you did your homework in 2nd grade, so you know the area of a rectangle is base times height. So we've got right here, we have got height. This is the height. Now the base is an easy one. That's just going to be this little thickness right here, which is dx, right? We're going to have dx be our thickness. So to find that height, to look at what we've got here, well, this height right here, if this were to go down, this is just f of x, right? If I know that y-coordinate right here, that y-coordinate is on f of x, so f of x is this height, but our rectangle stops here, so I need to subtract out this little piece here, but that piece is just g of x, right? So the height that we're going to have is f of x, take away g of x, it'll leave us with that height. So we're going to have over here, our base is just going to be dx, right? It's just dx, this little thickness here. And then our height is just going to be f of x minus g of x. Okay, so this is going to be the height of our rectangle. And then what we're going to do, of course, is we're going to sum all of our rectangles by using integration, right? Using integration, we'll sum all of these h times dx, and h is just f of x minus g of x. So for us, the total area will look just like this. The total area is going to be the integral from a to b of f of x minus g of x dx. That will give us our area. So we've got our formula right here for the area. And I just need to make a little note here. I'll put it in red because this is the important part. Note. It's basically top function minus bottom function. Meaning when you look at this picture, top function is f of x, bottom function is g of x, top function minus bottom function. So to find the area here, we just have to integrate f of x minus g of x dx between a and b. So the next case, case 2, in this case, we have f of x, which is positive, and g of x, which is negative. All right, so you've got this f of x above the x-axis, g of x below the y-axis, both, of course, continuous on a, b. And we are looking for the area, again, between a and b, and the area between f of x and g of x. So we'll do the same thing as before. What we'll do is we'll think of a rectangle. So I'm just going to draw a rectangle in here, a little sample rectangle. And we're going to find the area of this sample rectangle. And once you have the formula for the area of that one, then what we'll do is just sum all of them. Okay, so let's do the same as before. We'll figure out the area of our sample rectangle. We know the area is equal to base times height. Okay, so in this case, let's see, the height is going to be this whole thing here. The base, once again, will be this dx. So to find the height, well, we've got this part of the height. This is just whatever f of x is, right? Whatever this y value is here for f of x, that's this part. But then down here, we've got to figure out this length, that we want it to be a positive length, right? We don't want the y-coordinate here, which would be a negative y-coordinate, to add. So we're going to need to take the absolute value of this, because we're going to want to add f of x to the absolute value of this height, this y-coordinate, right? Because this y-coordinate will be negative. So what we really need for this part is not g of x, but the absolute value of g of x, right? We need the absolute value of g of x there. And then the height will be f of x plus the absolute value of g of x. Okay, so over here what we've got, base times height. Base again is dx. Now the height this time is going to be f of x plus the absolute value of g of x. And then what we need to do is think back to something that we've seen before. So we would have seen the definition of the absolute value in Calculus 1, and it's defined as a piecewise function. Let me redo that part. So it is equal to x if x is greater than or equal to 0, and it's equal to negative x if x is less than 0. So of course you can check that. If I were to take the absolute value of negative 3, which we know is 3, according to this, if this were a negative 3, I'm going to be down here because x is less than 0. So the answer to this is just going to be the opposite of x, which would be negative 3, which would be 3, of course. Okay, so if we do the same thing here, but not for x, but for g of x, right, the absolute value of g of x, well, we can model it based on the absolute value of x. It's just going to be g of x if g of x is greater than or equal to 0. And it's going to be the opposite of g of x if g of x is less than 0. Okay, so looking at this, when we're down here, g of x is definitely less than 0. So the absolute value of g of x for us is going to be negative g of x, right? So for us, the absolute value of g of x is negative, the opposite of g of x, because g of x is less than 0. Okay, so when we fill this in here, we're going to get dx times f of x. Now the absolute value of g of x is just negative g of x. So you go minus g of x. So then, putting the pieces together, the total area is just going to be this thing. This is our one rectangle, our sample rectangle. We sum all of the sample rectangles. To do that, we integrate from a to b f of x minus g of x dx. Okay, so this is our formula in this case. For case 2, we have this formula. I'll put a little gap here. So you can make a little note once again. The note here is really what we've got is top function minus bottom function. So it's the same as before. So it's the same area that we had before. Just take this top function, f of x, minus the bottom function, g of x. And if we integrate that from a to b, we get the total area between the two curves, just like last time. All right, so our final case, case 3. Case 3, we've got f of x and g of x, and they are both negative. Right, so here's the x-axis. F of x is a negative function. G of x is a negative function on this interval from a to b. Once again, we want to find the area between these curves and also between a and b. So once again, we come up with our little sample rectangle. Just going to draw a little rectangle in here. And to get to that rectangle, we've got this little direction, this little distance we've got to go here. But if you do the same thing as before, and we consider this over here, we want to find the area of our sample rectangle. And that is going to be equal to base times height, again, same as always. It's just a rectangle. Or in our case, base will be dx. Once again, this little distance here, the thickness will be dx. And this time our height is this distance here. So to get to the height, well, we're going to take this distance here. Now, because g of x is a negative number, if we want a distance here, a length, we need a positive value. So we'll take the absolute value of g of x here. This will be the absolute value of g of x. And then this little piece here that we have to subtract is going to be the absolute value of f of x. Right, so we take the absolute value of g of x to get this entire length. We subtract off the absolute value of f of x, which is this little piece here, and that'll leave us with the height. So back over here, we're going to have base times height, which would be dx times absolute value of g of x minus absolute value of f of x. Okay, now if you look at our previous definition of absolute value, you can see that in both cases, we have negatives here. So the absolute value of g of x is the opposite of g of x. Then we go minus. The absolute value of f of x is the opposite of f of x, or in other words, negative f of x. So we have this, and then right here we have minus minus, which most people learn now, minus minus, you just make it a big plus. So we've really got negative g of x plus f of x, which is the same as f of x minus g of x. So this will give us dx times f of x minus g of x. So that gives us the area of our sample rectangle. So then to find the total area, we sum all of our sample rectangles. And we will get the integral from a to b of f of x minus g of x dx. And that should look very familiar because in case 3, it's the same as the other two cases. If you look here, the note, once again, it's just the top function minus the bottom function in our formula. Looking at the picture, the top function is f of x, the bottom function is g of x. So top function minus bottom function, same as before. So in all three cases, it's all the same. Top function minus bottom function, f of x minus g of x. And that brings us to a definition. This is actually a definition. This is how we define the area of a region between two curves. So you've got these two functions, f of x and g of x, they're both continuous on this closed interval AB. F of x is greater than or equal to g of x in this region, which just means that this is the top function in the graph, right? If you look at the graph, since this one is greater than this one will be on top. So then the area between these two curves in this interval is just this form that we've seen before, f of x minus g of x. And a little note here is a little mantra that would be very familiar at this point. Top function minus bottom function, right? So when you find an area in between two curves, just look at which one's on top, subtract the one that's on the bottom, and then integrate that difference. So now that we've got a brand new definition, I know you're very excited to try it out. And here we go. Example 1. Find the area bounded by the graphs of y equals x to the 4th minus x squared and y equals 1 minus x squared. Well, this one we can probably come up with. If you think about y equals x squared, that's a parabola opening up, right? Smiley face. The negative makes it a parabola opening down. It would still go through the origin. And then y equals 1, we basically add 1 to that, so it's going to shift it up 1. So this one we can kind of figure out. This one, not quite as easy. You could play around with it if you wanted to, but if you just use your graphing calculator to get a picture of this one, and then you could plug this one in there too if you'd like. But I'm just going to draw what you'll see. And sometimes what you want to do, if you've got graphs that we're not as familiar with or as comfortable with, you want to put them in your graphing calculator. If nothing else, we need to see a couple things. We need to see which one's on top and when. And also, we need to make sure that they intersect. Okay, so look for which one's on top. If we're going to do top function minus bottom function, we need to know which function's on top. We also need to know what A and B are, right? A and B are where we're starting and stopping. So there's going to be a couple of points where these intersect, which typically we'll find A and B by hand. We'll just do some algebra. But first, let's look at a picture of these two graphs. So if you put those in your graphing calculator, you get a picture sort of like this. Yours will be a little bit better. Of course, this is just sketched by hand. But we can see that we want to find this area in here that's bound by these two graphs. So we're going to need to figure out where A and B are. A and B are where these two intersection points are. So what we're going to need to do, unless it says otherwise, we're going to need to find these by hand. Okay, we want to make sure as a Calc 2 student that we don't have to rely on our graphing calculator and do the intersect command or something like that. We need to be able to find these by hand for polynomial functions like this anyway. When they get too complicated where there isn't really a good technique to do by hand, so if there's like trig functions or square roots or something like that, then of course we'll use some other technique. But for most functions that we'll be working with, especially polynomials like this, we're going to want to find these intersection points by hand. So just think, to find out where graphs cross, what do? This is something we would have learned in algebra a long time ago. To find out where these two graphs intersect, if you remember, we just set them equal to each other. Okay, so that's how we'll find A and B. So let's find A and B. Okay, and we're going to want to do this by hand. Okay, find these by hand. So we set these equal to each other. So x to the fourth minus x squared equals 1 minus x squared. And then we can just solve this. So you can see right away that if I add x squared to each side, I'm just going to get x to the fourth equals 1, right? Just add x squared to each side of the equation, and the negative x squareds go away, so we're here. And then x to the fourth is 1. There's two solutions here, right? If you take the fourth root being even, I'm going to get a plus or minus the fourth root of 1. So basically from here we're going to get x equals plus and minus 1, which means that a is -1 and b is 1. So we're going to integrate from there. So to find the area now, the area is just going to be the integral top minus bottom, right? Top minus bottom between a and b. Well, a is -1, b is 1. And the top function on the graph, this is the top function, 1 minus x squared, minus the bottom function. The bottom function is this function right here. Okay, so I'm going to write something here. I want to see what you guys think. Is that good? Can I do it like that? Hopefully you are screaming at the screen saying, no, we can't do that. We need parentheses, right? We need parentheses because this negative sign has to distribute through. So this will give us negative x to the fourth plus x squared, right? So really we're going to get the integral 1 minus x squared minus x to the fourth plus x squared dx. Then we can see that minus x squared plus x squared will go away. So we end up with -1 to 1, 1 minus x to the fourth dx. So that's the integral that we would need to solve. And this one is pretty straightforward. You can use the power rule twice. We get x minus 1/5 x to the fifth between -1 and 1. So we plug in a 1 here at the top, and we'll get 1 minus 1/5 minus, I plug in a -1, we get -1 plus 1/5. Now, a couple of things I'll mention, okay? At this point, once we get here, you don't need to show me that you know how to do arithmetic. From here, you can just write the answer. You can just punch this in your calculator. Or you could punch this in your calculator and use that finite integral command on the TI-83 or 84 to get the answer. But I need to see this. Basically, what I want you to do, show me all the work you would need to do to show me that you understand calculus. All right, so we need to integrate to get here. Now, at the point where you can hand this off to an algebra student and they can finish it, you can hand it off. At this point, they can't finish it, right? Algebra students don't know the fundamental theorem of calculus, so they don't know what this means. So we need one more step. We need to plug this in, and then minus, then plug that in. When you do this, you're showing me you completely understand the calculus part of this problem. Because believe it or not, some people will reverse these. They're going to put the -1 in and then this one, or they'll put a plus. So I need one more step. I need this step. From here, you can just write the answer. Okay, so since I don't have a calculator with me, I'm just going to go through 1 minus 1/5 is 4/5 minus, over here I've got -1 plus 1/5. Well, this is like -5/5 plus 1/5, which would be negative 4/5. So this will be minus 4/5. So I basically get 4/5 minus 4/5, which is 4/5 plus 4/5, which is 8/5. Right? So again, this part here you don't need to do. You don't need to convince me you know arithmetic. I know you know arithmetic. Just show me you know calculus, right? Do the calculus part. I need this. I don't need anything else. From here, I just put the answer. I mean, I need the answer, of course, but you don't need to show me the arithmetic. The other thing is, you may have noticed that this is an even function. So what you could have done is, you can tell also by looking at it. Would you agree that if I integrate from -1 to 0, that's going to be the same as if I go 0 to 1? So what we could do instead, to make it a little easier, is just integrate from 0 to 1, and then double our answer, right? You can do this whenever you have an even function. Even functions like x squared or cosine of x, something like that, that is symmetric with respect to the y-axis. When you have one like this and these two numbers are the same but opposite signs, -1 to 1, that means that these two areas on this side and on this side are the same. So if you really wanted to, in this case, you could just go from 0 to 1 and double your answer, and you get the same thing. It's totally up to you. Okay, most students don't think of it, so most students will go through just like this. And then sometimes, if you look in the solutions manual, sometimes they'll do this, and students are like, "Where did that come from?" That's what they're doing. It's a little easier if you recognize this, but of course you don't have to do that. Sometimes in this section we will have to integrate with respect to y. So as an example, if a region's bounding curves are described by functions of y instead of x, then the rectangles that we use to approximate the area will be horizontal instead of vertical. And the area formed has y in place of x. So as an example, find the area bounded by the graphs of x equals y squared and x equals -2y squared plus 3. So x equals y squared, we can sort of see what that one's going to do, right? Because isn't it true I could just take the square root of both sides and get y equals plus and minus the square root of x? And y equals the square root of x, we know what that one looks like, right? That one's something like this. So then the negative of that would be the bottom part like that. So if you were to graph this function would look like this. And this is something similar. I mean, we can sort of see if it were reversed, if it were y equals x squared, it would just be a parabola along the y-axis. So when it's reversed, it's just a parabola along the x-axis. Now, of course, it's not a function anymore. It will fail the vertical line test. But this is something similar. We could do the same thing. This one's a negative, so instead of opening this way, it's going to open this other way. The 2 is going to tighten it up. It's going to be a tighter, less open parabola. And then also the 3 will shift it up here 3. So it'll go something like this over here. There's an easy way to find this on the calculator, though, using what's called the draw inverse command. And so when we get one like this, where we've got this function x in terms of y, sometimes the draw inverse command is nice to use to get our picture. So I'll show you how to use that, and then we can take the picture and go from there. What we can do is just go to y equals, make sure nothing is there, clear out any functions, make sure your plots are not highlighted, and then let's go to the window. Go to window, and let's set the minimum for x from -5, and then the max to 5. So -5 to 5. Make sure you use this symbol for the negative. -5 to 5. The x scale, that just means it's going to put a tick mark every 1 unit, which is fine. Then y, let's go -5 to 5, and 1 here also. Okay, so -5 to 5 for x and y. Make sure everything's cleared out here. And then what we want to do is we want to go to the draw command, okay? So you don't have to be in here. You can go second quit to get out of there. It doesn't matter. But we need to go to second program. And then what we're going to do is go down. On this calculator, it's the 8th one down, but we want draw inverse. So select draw inverse. And then I really want to draw x equals y squared. But what we do is just punch in x squared. It's going to do the inverse of that, which would be y squared. In other words, x equals y squared. So hit draw inverse x squared, hit enter, and that's that graph. And then go second quit to get out of there. And do the same thing again. So second draw, right? Second program. Go down to draw inverse. And this time we'll go negative 2x squared plus 3. Hit enter. And that's the picture that we'll use. Now just to clear those out of there, because they don't go out there automatically. So if you want to clear out your window so next time you graph those don't show up, just go second program again and just hit the clear draw and it'll clear them out. All right, so we've got a couple of graphs here from the graphing calculator. You can see this graph right here is x equals y squared. Oops, this graph here is x equals negative 2y squared plus 3. Then this graph is x equals y squared. So in this case, doing top minus bottom would not be very convenient because we'd have top minus bottom here, which they're actually the same function, which makes it tricky. Also, then we have two pieces because then we have a different top minus bottom over here, once again from the same function. So instead what we're going to do is we're going to have a horizontal rectangle that we're going to use for our approximation. So our rectangle now is going to be this rectangle here, this horizontal rectangle. So this rectangle here. So now the base of the rectangle is going to be a dy, right? The thickness here is the thickness along the y-axis. So instead of dx, it's going to be a dy thickness. And then the height, or the length of the rectangle, is just going to basically be whatever this x-coordinate is here, x sub 2, take away that x-coordinate, x sub 1, right? So the length of this rectangle, the length of it, or the height of it, if you want to think of it that way, is going to be x2, take away x1, and the thickness will be a dy thickness. Okay, so we've got this, this little dy thickness right here instead of dx. So if you think of this, if we were to take this rectangle out of here, the length of this rectangle is going to be the right x-coordinate minus the left x-coordinate. Now this right x-coordinate, that is from this graph here, right? That is from the x equals negative 2y squared plus 3. That's that x-coordinate. Now this x-coordinate over here is actually from x equals y squared. So we take the difference between these two, right? And that gives us basically our x2 from our picture, our x2 minus x1. And that means that the length x2 is basically from minus 2y squared plus 3. Then we're going to subtract x1, and that comes from y squared. And then the height, so we've got the length here of our rectangle, and now the height is going to be dy. So our area for the rectangle then is just going to be, we can actually clean this up a little bit, right? Minus 2y squared plus 3 minus y squared. That's just going to be minus 3y squared plus 3 times dy. You can also notice here, we basically have, instead of top minus bottom, when we have horizontal rectangles, it's going to be right minus left. The function on the right, which is this function, this is the function, the rightmost function, minus the leftmost function. So it's going to be very similar to before, but instead of top minus bottom, it's going to be right minus left. Okay, so then this will be the area of our rectangle. So to find the area of all the rectangles here, we just integrate. But we need to figure out where to start and where to stop. we need to find our, what we used to call A and B. Typically with this orientation, we just call it C and D. Same sort of idea, but we call it C and D. So let's find C and D now. Find C and D, and once again, we just have to set these equal to each other and solve, right? So we're going to say, where is y squared the same as negative 2y squared plus 3? Well, I could add 2y squared to both sides, and I get 3y squared equals 3, or y squared equals 1. And then, of course, take the square root of both sides, and you'll get y equals plus and minus 1. All right, so they're not always going to be plus and minus 1, just in case you're wondering, but we get plus and minus 1 again. So then the total area here, the area between these two curves, is going to be negative 1 to 1, right function minus left function, which we already did up here. This is right minus left, and we cleaned it up already. So that's just going to be negative 3y squared plus 3 dy. Now you can also see from the symmetry here, so we're integrating with respect to y, but from the graph you can see there's a symmetry here. So you could once again we have an even function. Instead of integrating this, if you really wanted to, you could integrate this from 0 to 1 and double it. Okay, but I'm not going to here. Just a little heads up that you can do that when you have even functions. And you can see when they're even geometrically if you could cut the area exactly in half. And when that happens, these will be the same number but opposite signs. So it'll be like negative 1 to 1, negative 4 to 4, or something like that. But in this case, it's pretty easy integral here. So we use the power rule a couple of times, and we get negative y cubed plus 3y. And then we integrate from negative 1 to 1. And that would give us minus 1 plus 3 minus, then you plug in the negative 1, you get 1 minus 3. And if you clean all this up, let's see, we get 2 minus negative 2, which just gives us 4. Okay, once again, for this class, go to here, right? When you go to here, you've shown me you know all the calculus, and then from there, I mean, this isn't too bad from here, but sometimes there's a whole bunch of arithmetic here. I mean, you'll see some of these problems, there'll just be a whole bunch of arithmetic problems here that we have to solve. We don't have to do any of those by hand. You can just use your calculator, right? But get to here. If you stop here, I don't know for sure that you know what to do, but if you get here, you've shown me you understand the fundamental theorem of calculus, which is f of b minus f of a, right? So go to this point. Okay, so that gives us 4. So the moral of the story for this one is when you have these functions x in terms of y, then instead of top minus bottom, it's going to be right function minus left function. For example 3, we've got a couple exponential functions to take a look at. So if you plot these two on a graph, you'll see we've got exponential functions, so they both go through here at 1. Because if x is 0, in each case you get y equals e to the 0, which is 1. So they both go through here. Of course, e to the 3x is steeper, so it starts down here and it goes up a little steep, and then y equals e to the x is more like this. So we are interested in the region between negative 2 and 1. So between negative 2 and 1, we basically have this area here between negative 2 and then 1. And you can see in this case, this is going to be a top minus bottom type of situation. But here to the left of 0, e to the x is on top and e to the 3x is on bottom. Whereas then when you cross over here, it's e to the 3x that's on top and e to the x that's on bottom. So we're actually going to need two integrals here. We're going to need two integrals. One from negative 2 to 0 of top minus bottom, and then one from 0 to 1 of top minus bottom. And we should, just for practice, let's still find this intersection point. It looks like they're going to cross here at 0. But let's just for practice, let's always find this by hand. So let's say we're going to find the intersection point. Okay, sometimes the software just does things like that for some reason. Just changes the screen a little bit. But okay, let's try to find this intersection point. So we'll set these equal to each other. Okay, this will be a good practice for us. E to the 3x equals e to the x. So we are solving for x. Now we can see just by looking that if I plug in a 0, they're going to be equal. But just for practice, if we're going to solve for x in an exponent, that's when we use logarithms, right? Because we basically, if we take in this case, let's use the natural log, so log base e. If I take the natural log of each side, we'll get something like this. Natural log of e to the 3x equals the natural log of e to the x. And then we can use this rule of logarithms that says if you've got, now this could be any base, I'm just using natural log, which is log base e. So natural log of a to the b, remember we can take this exponent and turn it into a multiplier. We can bring the b down and multiply. Right, so that's what we can do here. So once you take the natural log of each side, we can bring these down. So we'll get 3x equals x. If I subtract x from each side, I get 2x equals 0, right? Which means, of course, x equals 0. So we're just finding the intersection point by hand. So it does, these cross at 0, which means we're going to have two integrals here. And we just have to find the area, just add the two integrals together. So the area is going to be, the first integral goes from -2 to 0. Right, we saw that they intersect at 0. Sort of knew that before, but again, this is just for a little practice. So we're going to start from -2 to 0, and it's going to be top minus bottom. Now the top graph here is e to the x. So this is going to be e to the x minus e to the 3x, which is the bottom curve. Then we have to add on to this the second part right here, this region here, which goes from 0 to 1. And the -2 and the 1 are from here, right? X equals -2 and x equals 1. So we're looking at the area bounded by these four parts, right? So that's where the -2 and the 1 come from. So you go 0 to 1. Now top here is e to the 3x. So this is going to be e to the 3x minus e to the x dx. And when we integrate here, well, the antiderivative of e to the x is just e to the x. And then here, you have probably seen enough u substitution for something like this, just from Calculus 1, to know that we're going to have to deal with this 3 here, right? And we deal with that with a 1/3. So I'll just do this just in case you need a little practice. Let's say we've got this, just this by itself. Let's say this is our question. In Calc 1, we would have done a u substitution. We'd say, well, u is 3x, and then du is going to be 3 dx. So then 1/3 du equals dx. So that means we can swap out the dx here. We can get rid of this dx and swap it out with 1/3 du. And then this is, of course, going to be e to the u. So our new integral would just be 1/3 e to the u du, which of course, once we integrate, we get 1/3 e to the u plus c. And then we would just plug back in our u, which is 3x. And we would get 1/3 e to the 3x plus c. Okay, so that's just over on the side. So moving that over here, we're going to get e to the x minus 1/3 e to the 3x. Now, here, this just little sample problem was, we're going to get a plus c because this was an indefinite integral. But here we've got a definite integral, so we have to evaluate between -2 and 0. And then very similarly over here, we're going to get 1/3 e to the 3x minus e to the x, this case from 0 to 1. Okay, so now we can plug in 0. So we will get e to the 0 minus 1/3 e to the 0 minus e to the negative 2 minus 1/3 e to the negative 6, right? Because I plug in negative 2 here, so I get negative 6. Okay. And then we've got plus. Now I'm over here. I'm going to plug in 1 into here. So you get 1/3 e cubed minus e to the 1 minus, and I plug in a 0. Plug in a 0 here and here. And we will get 1/3 e to the 0 minus e to the 0. All right, now as we know, anything raised to the 0 power is just 1. So we can clean this up a little bit. This should be 1 minus 1/3 minus, we're going to distribute this negative through here and here. And we will get minus e to the negative 2 plus 1/3 e to the negative 6 plus 1/3 e cubed minus e. And then here, again, anything to the 0 power is 1. I'm going to distribute the negative through, so we get negative 1/3 and then plus 1. All right, so let's see if we can clean this up a little bit. So we've got 1 minus 1/3, and we've got plus another one. So 1 plus 1 is 2, minus 2/3. Let's see, 2 minus 2/3 would be like 6/3 minus 2/3, which would be 4/3, right? So 4/3, 4/3 is just from, we can do it like this too, 1 minus 1/3, that's 3/3 minus 1/3, that's 2/3. Then over here I get another 2/3, right? So that's 4/3. And then we get, this is just kind of an unusual looking answer. I guess it's just going to be kind of weird. We get minus e to the minus 2. And then plus 1/3 e to the negative 6 plus 1/3 e cubed minus e. So just kind of an unusual answer for this one. And this is usually what we'll be looking for. We're going to be looking for the exact answer, because typically it takes more skill to get the exact answer than to get a decimal approximation. Now, if you do get a decimal approximation, it's going to be a little over 5. I think this comes out to be about 5.176. So it's roughly 5.176. So you could check your answer just by using finite integral on the calculator right from here. And of course, that will give you the decimal approximation, which should agree with this. So you can always check them on your calculator. So the main takeaway from this section is when you're going to find the area between a couple of graphs, you just need to see which graph is on top and which is on bottom, or which one is on right, which one is on the left, right? So having a picture of what's happening is kind of the key to this, and then it just takes a little practice. Also in the homework is going to mention the midpoint rule. So I just mentioned this. I think one of the problems asks us about the midpoint rule. It's something that you typically cover in Calculus 1, and we'll see it again also in Calculus 2. But it's in, if you want a little review, it's in section 5.2, okay? And that is on page 390 if you have the 9th edition of the book. 9th edition of Stewart. If you have the 8th edition, it's on page 384 in the 8th edition. Okay, so that should give you everything you need to get started. And now you know the key is, the only way to get good at calculus is to do calculus. So make sure you try those homework problems and just try them out. And of course, if you have any questions, let me know.